We will now look at a new type of algorithm design principle called the greedy method. Many algorithm problems are actually optimization problems. So in such problems, typically we have some kind of universe or a set of objects, and we have to choose some subset of u so that we maximize, or in general it may be minimize also, say optimize some objective function. So an objective function is just some kind of measure. Okay, it will be cost or distance or quantity, and so we have to choose a set which maximizes or optimizes this function according to what we are trying to achieve. So let's look at some examples. Okay, so the first example might occur if you are moving house. Okay, so if you ever moved house, you would know that you pack all your things into cartons, and now if you travel from one city to another, typically the cartons go by container. So a container is a large cuboidal box which can be loaded onto a truck or a train. Now suppose you can have only one container. So you don't have an unlimited capacity to transport things from one city to another. So you can only load one container, and you have a bunch of cartons, and all the cartons presumably don't fit. So each carton is of different size, and also each carton has potentially a different value. Some may have your books, some may have your kitchen stuff, and so on. So now here the optimization problem is the following. So you have to pick a subset of cartons to load into the container. Right? So this is the problem, to pick a subset. And what is the objective function? You want to maximize the value. You don't want to leave too many things behind. And if you judge things based on some notion of value, you would like to pick a subset of cartons to load into the container such that they fit, of course, and you maximize the value. So this is one possible version of an optimization problem. So let's look at another example. Okay, so suppose you are kind of working from home, so you're kind of a freelance, say you're an artist, okay, and you get project offers from people. So people come to you and say, would you design this cover of this magazine for me, would you design this poster? So each job has some revenue, some profit for you if you do it, but each job also takes time and has a deadline. So it might take you 2 days to make a magazine cover, 5 days to make a poster, and so on, but each job has to be finished within a given time, and if you exceed the deadline, there is no profit. You don't get paid. Okay. So now here you have various jobs with different profits and different deadlines, and you can only do one job at a time. Okay, so you have the constraint that you can't work on more than one job at one time. So now what you want to do is you want to choose a set of projects to take on so that you maximize your profit, maximize your earnings or revenue, right? How much you get from these jobs. So the idea is that each of the projects that you take on, you'd better finish it within the deadline, otherwise you're not going to get paid. So you want to choose an optimal set of jobs. Right? So how does one solve these kind of problems in general? So there is a natural brute force approach, and this is to just enumerate every subset, right? So you have a subset of things that you want to pick up a subset of things, so you enumerate all subsets. Okay? And after you've enumerated all of them and you evaluated all of them, choose the best one. Okay? So you don't know which contract to do, so you say, okay, I will try all possible sets of contracts, and then among the set of contracts that gives me the maximum revenue, I will pick that one. or I don't know which set of cartons to put in the container, so I will try all possible sets of cartons that fit, and the one that gives me the maximum value that goes into the container, that's the one I will transport. Okay, now what's the problem with this? The problem with this is that if you have n objects, okay, then you have 2 to the n subsets, because you have to try out every subset, first check if it is feasible. I mean, for instance, if you can actually complete all the jobs within the deadline, or if you can actually fit all the cartons into your container, and then you have to evaluate, once it is feasible, what is the cost or the objective function for that subset, and then pick the best one. So clearly this is an exponential algorithm in terms of the number of objects, right? So this is not a desirable strategy. On the other hand, sometimes we can do better. We can be greedy. So what we can do is we can just select at each time one object. How do we do this? Well, one possible way is that we fix an order to begin with. So for instance, we might decide to choose the biggest carton first, then the next biggest, and so on, and try it out. Okay? Or we could periodically check which is best. For instance, if we have selected a bunch of jobs that we are going to take on as an artist, then we might decide to choose the next job which is earliest among the jobs that we have not yet chosen, and among those has the best profit, or something like this. So we have some criterion by which at each point we can uniquely pick a next job. And now, having picked this next job, we check its feasibility. Can I add it to the collection that I already have and not violate anything? So can I put this carton into the container and not make the container overflow? Or can I choose this contract and not fail to meet any deadlines to jobs I've already committed to? Okay. And if this greedy strategy is the correct strategy, then what you will find in the end is that you have an optimal subset. Okay. So this is called greedy because you make a purely local choice. You don't look ahead. You just pick the best one that's on hand to choose next, and you never go back and change your mind, right? So you just pass once through your set of objects. So you make a single pass, okay? So you don't ever go back. So you make a linear scan, one scan. Of course, each step of the scan may take a little more time, but still it's very far from exponential. If you have n objects, you're going to take n times the number of time amount of time it takes to evaluate the feasibility and the cost of each object. And what you're guaranteed is that if you do this and the greedy strategy is actually correct, then at the end, in this linear scan, you would have found the optimal solution. So of course, as you would imagine, not all problems admit a greedy solution. If they would, then life would be very simple. So let's look at a couple of problems, not the ones we saw before, but a couple of different problems which actually do admit greedy solutions. So the first problem is one of making change. Okay, so you are a shopkeeper and a customer has a bill of say rupees 247, say, and you have to give change because he only has a 1,000 rupee note. Now you are very possessive about the notes and coins you keep in your drawer because you have to keep making change. So you want to return the minimum number of notes and coins. Right? So the problem is to make change for this 1,000 rupee note where the bill was 247, giving a minimum number of notes and coins. And of course now we have to define the set of notes and coins that we are going to choose. So we're going to get a subset of notes and coins from some set. So we'll assume that we have the usual denomination. So we have 1, 2 and 5 rupee coins, and say we have 10, 20, 50, 100 and 500 rupee notes. Okay, so this is what we have to choose from, and now we have to choose the minimum set. Okay. So what one possibility is to try all possible ways of making up. So remember, the change now is rupees 753. That is 1000 minus 247. So we have to make up 753 rupees using this. So we can try all possible combinations and see which one gives us the smallest number of coins and notes put together. But of course, that's going to be an inefficient thing. So let's look for a greedy strategy. So here is a greedy strategy. What we will do is we'll try the largest denominations first. Okay. So we start with 753, and then we have the largest denomination is 500. Okay, so 500 is something that will go in 753, and then what happens is that we can only use one 500 rupee note, because if we have two 500 rupee notes, we exceed the amount we have to return. So we say, okay, we can put one 500 rupee note, and now the balance becomes 253 rupees. So now we can't use any more 500. So now we go to the next denomination in descending order. So we find that the next denomination is 100, and the 100 rupee note will fit in 253, and in fact, two of them will fit. Right? So you take 200 rupee notes, and you come down to exactly 53 rupees. Now your next denomination happens to be 50, so you can put in a 50 rupee note and one of them. Right? And now your balance comes down to 3 rupees. Now you see that if you try the next denomination, it is 20. Unfortunately, you can't do it, so you have to discard it. This is not feasible. Right? Similarly, 10 is not feasible. Okay, now you come down to your coins. 5 is not feasible. And finally, you come down to 2 and you say, aha, I can use a 2 rupee coin. I can use one of them, and my balance is now 1. And now I'm left with one last denomination, which is 1. And again, I can use it, and I can get one of them. And so finally, my change making solution is to put one 500 rupee note, 200 rupee notes, 150 rupee note, one 2 rupee coin, and one 1 rupee coin. Okay. Now, the point to make is that I never go back. I don't go back and say, oh, I couldn't use a 20 now. Would it be possible to use a 20 now if I went back and did not put a 50 before? Right? We never have to backtrack and change an earlier decision. So we just make a decision one at a time, and at each point, the thing we choose next is given by some simple criteria. Here we actually just in advance fix the order 500 down to 1. Right? So we just pick the largest denomination one at a time, and we try to order it. Okay? So in this example, we end up using 6 notes and coins, and you can check that you can't do any better. In fact, no matter how much the change is, if we are using this collection of notes and coins, the greedy strategy will always use as few coins and notes as possible. Now, is this always the case? Well, supposing we had a different set of coins and notes. Supposing our denominations were 250, 100, and 1. And suppose we need to return 400 rupees. Okay. Now, if we follow a greedy strategy, you would first put a 250 rupee note down, then you would put a 100 rupee note down, so now you have 50 rupees to return, and then because you have no other choice, you will have to put 51 rupee coins. But the optimal in this particular case is 400 rupee notes. So clearly the greedy strategy fails if we have a different set of denominations. So this is a general problem with greedy. So greedy correctness needs a proof. The fact that a greedy strategy actually produces an optimal solution is not always clear. In this particular case, for change making, the optimality actually depends on the denominations. So it works for some denominations, like the one that we used before, it works. For this denomination combination, it does not work. Now we are not going to prove it here. We will prove it for different algorithms, how you show that a given strategy is optimal or not optimal. But all we need to observe here is that greedy on its own needs a proof in order to be justified. Okay, so let's look at another problem. This is one version of a very familiar type of problem that you come across many times. So it's called task scheduling. There are many different task scheduling problems. So one of the task scheduling problems was the one we looked at earlier. So you are a single person, you have a bunch of projects to take on. So how do you order them so that you can meet the deadlines and make a profit? Now this is a different problem. So here you have some jobs, okay, so you have some tasks, okay, and you have some machines. Okay? So say you have n tasks, okay, so you have tasks 1 to n, and you have some machines. So now each task okay, has a duration. Okay, and the machines can only do one task at a time. So what this means is that if you have overlapping durations, you cannot assign, you must use different machines. Okay? So in the worst case, if all the tasks overlap, then for these n tasks, you would need n machines at most, because you can assign each task to a different machine. But sometimes if one task ends before another task starts, so each task has a fixed duration, it has a starting time and an ending time. Supposing one task begins after the second task is ended, then you can put the second task onto the same machine as the first task, because the first machine is free now. So the goal is to allocate tasks to machines, but to minimize the number of machines. Right? So we want to use as few machines as possible. So we know at most we need n machines, but we could possibly do with much fewer. So here is an example. So supposing we have 7 tasks A, B, C, D, E, F, G, and each task has a starting time and an ending time. So A starts at 0, ends at 2, D starts at 9, ends at 11. So for instance, if we use a machine for A, we can reuse that machine for D for sure, because 2 is before 9. On the other hand, B and C start at times 3 and 4 and go on to 7. So B and C overlap. So we cannot possibly use the same machine for both B and C. So our goal is to now find a minimum number of machines to allocate to complete these 7 tasks. We know that 7 machines will do, but hopefully we can do with much fewer than that. So one way to think about this is to process the tasks one at a time in order of starting time. So we start with the first task that we have to work on, okay? And then we look at the second task and so on. So let's do that. So let's reorder these tasks in the order of their starting time. So if we do this, we now have the following order. A is first because it begins at time 0, and then F is next because it begins at time 1, and B starts at time 3, and so on. So we have the order A, F, B, C, G, E, and D. So let's work through the strategy, and then we will describe it a little more formally. So what we do is we say, okay, we have to start A somewhere. So we start with, say, machine 1, and we let A run, okay, from time 0 to time 2. We have job A. Now we come to F. Now F starts at 1, which is during the time that A is working. So we have to use a different machine. So we go to a new machine M2, and we start F at time 1, and we let it run till time 5. Okay. So now this is 1, and this is 5, and this is the task F. Now we come to machine task B. Now B starts at time 3. At time 3, machine 1 is now free because machine 1 has already finished its job at time 2. So we can reuse this machine. We don't need a fresh machine. Right? So this is the kind of optimization that we would like to do to minimize the number of machines. Reuse a machine whenever it's possible. So we start at 3 and say we go on till 7. Right? So this is our task B. So far we have used only 2 machines for 3 tasks. Now we come to task C, and now task C is going to start at time 4. At time 4, B is running and F is also running. So here, unfortunately, we have no choice but to start yet another machine. And C is going to run from 4 to 7, the same time when B ends. So we can put a third machine into operation from time 4 to 7. Right? Now we come to task G. Now G starts at 6. At time 6, M1 and M3 are both occupied, but M2 is now done. So we can start a task here and let it run to time 8. Okay. So we can assign task G to machine 2, which has finished processing F. And now we come to task E. Task E starts at 7. At time 7, both M1 and M3 have finished. So we are assuming that if a task ends when another one starts, we can immediately reuse that machine. So task E can now go on M1 or M3. So let's just decide to put it on the smaller number machine so that we have a unique choice. So we say that E will now go on this machine from 7 to 10. And now we come to D. So D is at time 9. At time 9, M1 is in use, but M2 and M3 are both free. Once again, we will decide to use the smaller of the two just to be unique. And so we have 9 to 11. Okay. So we have constructed actually an allocation and also marked out the times to show that they don't overlap. And in this case, we have used 3 machines. Okay. Now, of course, the claim is that this is optimal. How we show that this is optimal or our previous strategy for making changes optimal is a different issue. We will describe proofs when we come to more examples later on. But for the moment, this is just to illustrate how a typical greedy strategy works. Right? So in this case, what is the greedy strategy? The greedy strategy is first you order the jobs, order the tasks by starting time. Okay, and order in what order? Well, order in ascending order or in not decreasing order. Okay. And then for each job, okay, so what we have to do is we allocate it to the smallest numbered machine that is idle. There's always such a machine because, as we said, we assume that we always have at least n machines for our n tasks, right? So if nothing else is free, we can always get a new machine for each task. But in the best case, we will actually reuse a machine which has already been in use.